Question number 1. For a certain harmonic oscillator with a given effective mass, the difference at adjacent energy level is also known. Calculate the force constant. So first, Z means 10 to the minus 21. So under harmonic oscillator approximation, the allowed energies is Planck constant times nu, which is the natural frequency, times V plus half. That's the allowed energies. Using this equation, you can calculate the difference between adjacent energy level to be h times nu. And nu is 1 over 2 pi square root k over mu. So we have effective mass. This is given. We have energy difference, so we can calculate k. So modify this equation. So k is 2 pi over h delta E squared times mu. Okay, plug in everything, and that gives you 278 Newton per meter. Question number 2. Sketch the form of wave function of the harmonic oscillator with quantum number v equals 0 and v equals 1. Okay, so this is similar, the wave function shape similar to the 1D box model. So if you remember 1D box model, so the first one, n equals 1, it's half wave. And the second one, n equals 2, you have one wave. Okay, so similarly for vibration, harmonic oscillator, here the quantum number first one is not 1 but 0, and then v is 1. And you see the first one is also half wave. The difference is in the 1D box model, it ends at the two ends. The wave function are 0 at the two ends. Here, it penetrates a little bit further away from the forbidden region into the forbidden region. Similarly, when v equals 1, you have one wave, but also extend beyond the forbidden region. So use a symmetric argument to explain why these two functions are orthogonal. Orthogonal means two functions product integration is 0. So look at the first, this function is odd number wave function. This is even. When they multiply each other, you get an odd function. So the product of these two functions is an odd function. And therefore, the integration will be 0. Question number 3. How many nodes are there in wave function of a harmonic oscillator with V equals 3, V equals 4? So this is the energy diagram of the first 4 energy levels and the wave functions. Compare with 1D box model. So the first energy level, which n equals 1, half wave, okay, similar to this one, half wave. And then second one, it's n equals 2, and you have one wave. So in this case, the first one, you have no nodes, and the second one, you have one nodes. So in 1D box model, the number of nodes equals m minus 1. Now in harmonic oscillator, the first energy level V equals 0. Again, it has no nodes. And then V equals 1, you have one nodes. V equals 2, you have two nodes. And therefore, in this case, the number of nodes equals V. Okay, compared to the 1D box model is m minus 1. M minus 1. Here is V, just V itself. And therefore, when V equals 3, the number of nodes is 3. When V equals 4, the number of nodes is 4. Question number 4. Calculate the wavelength of the photon needed to excite a transition between neighboring energy level of harmonic oscillator with effective mass given, and the force constant also given. So for harmonic oscillator, the allowed energy level is hv times hν times v plus half, and the energy difference between adjacent energy level is h times nu. All right, so that's the equation for the energy separation. And if the molecule absorb the photon, and the photon energy has to match this one, so it's h times c divided by wavelength. That's the wavelength of the photon. So using this equation, modify it, we can calculate the photon wavelength. All right, and the effective mass is given, the force constant is given, so we can calculate the wavelength. Now, there's an alternative way to calculate this equation, this question, and that is, we know on the harmonic oscillator, the absorption wavelength, frequency should equals to the frequency, natural frequency of the oscillator, which is 1 divided by 2 pi squared root k divided by mu. So this is absorption wave frequency, and this is natural frequency. So these two should be the same. And in order to calculate wavelength, okay, wavelength, we should use speed of light divided by this frequency. And that gives you the same equation. Question number 5. Indicate which of following molecules show vibration absorption in infrared. Okay, so in infrared we have a selection rule, that is, the molecule must change dipole moment when they vibrate. So looking at these molecules, HCl, when they vibrate, the change bond length, that will change dipole moment. So this will give you vibration absorption. But nitrogen gas does not, because it does not have a dipole moment. Similarly, chlorine molecule does not change dipole moment. And DCl is similar to HCl. Water is a dipole molecule, and so when they change bond length, they change dipole moment. And the CO2 is a symmetrical molecule, but because you have 3 atoms, there's a mode, as we saw in the lecture notes, that can change dipole moment. So it also absorbs vibration in infrared. Okay. So the answer is HCl, DCl, water, CO2. Next question. The fundamental vibrational frequency of HCl is given. Calculate the force constant. All right. So under the harmonic oscillator approximation, and this frequency should equals to 1 over 2 pi square root k over mu. Okay, equals to natural frequency. So in order to calculate the force constant, we need to calculate the reduced mass. Okay, so first calculate the reduced mass, and remember this is to change molar mass into grams per atom or per molecule. And so with this reduced mass, we can calculate the force constant, that is 510 kilogram per second squared. Okay. Now here it asks you how large a mass would be required to stretch classic spring with this force constant. So we imagine the molecule bound like a spring with a force constant equals 510. So with this spring, how much force do we need to stretch displacement 1 centimeter? All right, so we use Hooke's law. Force equals k times x. X is the displacement, is 1 centimeter. Force constant is given, is 510, and so the force can be calculated. Now force is mass times gravity, so that's the weight, all right, and therefore we can calculate the mass. So mass is 0.5 kilogram. So imagine the bond, so tiny, all right. In order to stretch 1 centimeter, you need 0.5 kilogram of a mass. Question number 7. So this question is about enharmonic vibration. So for enharmonic vibration, you not only you can see the absorption due to the 0 to 1 adjacent transition, and that's the fundamental absorption. You also see the overtone, which is go from V equals 0 to V equals 2. So delta V is not 1, but 2. You can see that even though it's weak, okay, you can still measure that, and that's this number. And the second overtone, 0 to 3, and that is also very weak, but you can still see it. So using these numbers, we want to calculate the natural frequency of the vibrator and the enharmonicity constant. So the theory predicts that the transition between energy levels is calculated by this equation, and this is a harmonic oscillator, and this is enharmonicity with enharmonicity constant. So using this equation, and as we show in class, we show that the fundamental transition from 0 to 1 should equals to this equation. This is the natural frequency and harmonicity constant. So two unknowns, and this can be measured by infrared to be 1556.22. So you have one equation, two unknown. And then the first overtone, by theory, all right, we can show it's again two unknown, okay, natural frequency and enharmonicity constant, and measured number is 3088.28. So two unknown, two equation you can solve, even though you have a second overtone. But in order to calculate V nu and Xe, we only need two equations. So two equations, we can solve it.